My name is Wang Ziyang. Today I'm very happy and here to share my report. And actually, this time I'm not a very strictly report for me. I just to report this period from September 12th to November 11th, what I did. So what I did in this period, I do some theory. My theory is about a solution for non-transferable utility cooperative differential games. So and the second is what I read as reference, and the third is my programming, and then there's some Russian language. And the second part, I want to show you my plan. And about theory, I learned these three solutions, and this is a Nash Budget solution, and it need to satisfy this four axiom, and it's the solutions formula. And then I learned the K9 small Rodinsky solutions, and the third one is the Ignatiorial Budget solution. And this is the solution, the comparison. Can see the Nash Budget, KS, and the K9. And we need to send, and the Nash, we need to satisfy this four situation. And sometimes they can't satisfy some situations. And the second part is what I read some reference, like this reference, and I also added the link, and what's the reference model, the aim, the conclusion, and my some ideas. And I don't know if.
But it's just interesting, you know, for everyone, I think.
Yeah. Yeah, I agree with you because this reference is very, very interesting because actually it's not referring the March theory, but it's just an idea. It's not because I found some solutions application to find this reference, but in there I'm not found application, but I found a very, very interesting idea. So it uses game theory's knowledge to improve the students' efficiency in the class. So if somebody have interesting, we can do some experiment to accomplish this idea to true, maybe. And the second reference I do like this.
Sorry, how to improve efficiency? Can you say few words? Using what? Using cooperative game theory, right? How?
Just yeah. Words. In that, okay. In that articles, okay, go back. Okay, I just said to us. In that articles, they divided all classes. You know, the Chinese classes, they always have 30 or 40 students. So they can divide the students into several parts, and different parts they need to finish some achievements. Like if we want to learning an axiom, we need to know the concept, and then we need to know the solutions and how to applicate it. So maybe we can divide the different groups and the cooperative. The first groups, they just maybe their scores not very high. They are not very good foundations. So the first groups, they just know about the concept. And the second group, they not only the concept, they also need to know how to use it. And the third maybe can give you a report. But every part, all students all need to finish. They just how to say, the teacher just like a guidance, but the work actually need the students do themselves. They have a team. So maybe at this not only can improve their cooperation skills, it also can make them knowledge more how to say, more more deeply in their hair and know how to use it. So maybe it's a very interesting methods. And if I want to come true these ideas, I want because we have many classes. Maybe one classes we can just use the normal teaching style, and the second we use this idea. So and the last we can give them some exactly criteria to compare the students how much they get their knowledge, and to give their scores, and maybe it's just my very basic ideas, and just very interesting about it. It's
But it is
okay.
not all like this, right? It's not all like this. You should also introduce some KPIs to because
Yeah.
you need to each team member or class mate should know how his KPI will be calculated. So in the class where there is a cooperation, you want to calculate his KPI or mark or grade using some cooperative solution such as Shapley value, right? Yes, so that's the key point, how to apply cooperative game theory here, right? That's the key point. Am I right, or I'm correct or not correct?
You're correct, because I said some goals last time. I said in the similar and the last, maybe we have examinations. Although we use a different style to teaching the students to two classes, but we have the same examination, and then we can get a student's mark to compare it's possible or not.
Okay, thank you very much.
Yeah.
Very interesting,
Okay.
Thank you.
This is another cooperative, another reference. The name like this, also and the link. If you want to see, I can show you. But I think this time is very urgent. And this, after reading this is why they do this, and this is this reference model, and they use which methods and the results. Thinking. Actually, the power system is not my application direction, but after reading this reference, for me, I think the matrix is really useful. And this article also uses Shapley value to judge which link is more important. Okay, in this article, I have some problems, and I mark it. If we have time, I think after similar, we can discuss about it. And the third unraised reference is I want to find the application about budgeting solutions. But this reference is very how to say about 1970 years. It's very very basic formulate process. In this article, just from writing aspect, I think the singles of strategy and trajectory in this article changed many times. So it's not easy for readers to understand. So in the future, I think when I'm writing, I will try use the same singles and the same concept. I think it's more better. Yeah, it's just my thinking. And
it's no problem. Yeah. Actually, why I suggested this paper is because it's a very basic paper.
Yeah.
For and when you read this, then you can understand how to apply. Okay.
Yeah, and when the next year, you give me some topic, and I need to plot some figures, use the math software. And so this year, you also suggest me to learn some data science, some programming. So I learned the Python basic lectures, and this is under the online courses, the website. Actually, it's not similar. Under the other students use this website, and I clicked in and think, oh, it's very easy for me. It's more easy for me to study it. So and this time I finished 1, 2, 3, 4, 5 models, and I think I will continue. Actually, this time I already finished the Python basic lectures all. As a meanwhile, I also learning some Russian language by myself. So by the way, so let me check. I need to say words. I need to say Stenium Nargenia.
Thank you
able
very
and
much. Thank
using.
you.
Yeah.
Thank you. Thank you. Thank you very much.
Okay, the next step, map 9, about the theory, I need to find some, you see the subgame consistency, and I need to search some interesting direction application and some relevant papers and book for application. This is just for my theory, and of course, I know this time theory is more important, and at the meanwhile, I will still continue to learning programming languages and the Russian language. It's all. Thank you. Thank you for your attention.
Of course. Thank you very much. Thank you. Thank you. That was great. I think perfect presentation, even some ideas from different papers, and that's very great. That can give us some thinking. Thank you very much.
Thank you very much.
Okay. Okay. But anyway, we need to have some discussion. Maybe not after this meeting, but maybe Tuesday or Thursday.
Okay.
To understand. Okay. Thank you very much. Thank you.
Goodbye.
Thank you. Goodbye. Thank you.
Alnas?
Yes.
Alnas? Професор Ли и другие преподаватели сейчас в клубе. Вы можете по-английски передайте привет.
Oh, okay. Professor Li, are you here?
李老师。
Hello, everyone. It's very nice to see you. Long time did not hear you. We are already for about 3 hours of the seminar, and I think most of the students are doing very great. Sorry, our webcams, most of the participants' webcams are off because it's very hard for the internet to share presentation and do some talking. So, but I think it's great. We have almost 50 participants and a lot of people are interested. I'm happy that this seminar is working, and I'm very happy that Dr. Lin helps us, and that's very great. He's doing great contribution. Also, he is very involved in all of this research, and yeah, I think this is it. How are you? How is Yan?
他问一下李老师、薛老师还有其他老师，怎么样？你们能听到吗？
Hello. Sorry, I'm later. Sorry.
No problem.
Later. Yeah, nice to meet you.
Nice to meet you. No problem, because we are recording the video, and we will send. I think we will send you the video for all 3 sections, and
okay.
I think it's okay. It's okay if you miss some part, because if you're interested, you can have a look again. It's very good. So,
okay.
Yeah. Okay. Okay. So if you want, you can listen to other presentations. So, может быть, мы продолжим, или хочешь еще что-то сказать?
李老师，你有什么想说的吗？
没有啥，我就是今天，因为咱们那个啥，韩红俩不是结婚嘛，回来先我一下忘了，今天有点感冒，所以来的迟了。没事，我就是听一听。
没关系，
这个挺好的，以后多组织。
对，那个我不知道是韩老师今天结婚，所以我们之前很早之前是2周前上定的时间，所以那个什么就是可能让老师们多有不便。
对，今天刚好碰到一块儿了，周末，你想
我们想着可能
点
周末大家还有时间，结果没想到就是也挺不凑巧。不过真是韩老师的大喜的日子，因为之前看他朋友圈，以为他已经结婚了嘛，朋友圈发过照片。
但是，没事，挺好的。
好的。
我就突然想起来，哎呦，我说我赶紧进来看一眼，也不好意思。
没有，
昨天还
特别欢迎您过来。 那我跟他说можно мы продаем?
Of course, I'm very happy to continue because it's already 3 hours. I hope we can finish soon.
So 3 students.
Okay, okay,
Last.
okay. Let's move on. Let's move on.
大家剩下3位同学可以快一些啊。然后第一位是周江静。
Yeah, hello.
Hello, hello, hello.
Yeah, hello everyone. And the topic I'm talking today is a game model based on uncertainty and learning. So let's start with the content. The first one, I want to introduce some relative concepts, and then I'm going to talk about the books which I learned. And the third part is the main theorem, which we are going to apply. And the next part is the papers which I learned. And the last one is for the further plan. Let's start with the first one, some relative concepts. So the main concepts which I learned are as following. They are conditional probability, total probability theorem, and Bayes rules. I'm going to introduce this one and also the sufficient and support parameters of the probability distribution function. And the last 3 one for information learning, no learning is in the model. So I'll introduce them later. And what's the Bayes rules? Bayes rules, it's also called the Bayes theorem. It's stated in the following equation. The PAI vertical line B is the posterior probability, and the PB vertical line AI is the conditional probability, and the PAI is a prior probability. So these two is more important, and the PB is a normalization factor. We can use the total probability theorem to turn PB to this one. It's a sum of all the keys of AI. And next, we will turn to the sufficient statistic and support of the probability distribution function. What's the sufficient statistic? A statistic is sufficient if no other statistic that can be calculated from the same sample provides any additional information. And what's the support of the probability distribution function? Here is the definition. By the definition, the support doesn't contain values that map to a probability of 0. And the above are the concepts which we will use in the papers. And then let's share the books that are relative to the model. There are 2 books. The first one is the Handbook of Dynamic Game Theory. The author is Professor Basser and Professor Zakor, and I learned the main chapter 4 is about the multi-stage games, and the second book is the subgame consistent economic optimization, and the author is Professor Yang and the Professor Biluo Xiang. And the main chapter which I learned is the dynamic consistency in discrete time cooperative games. And there are the third part is about the theorem. It's a theorem for the discrete time. The theorem is the necessary and sufficient condition for a feedback Nash equilibrium. Maybe I will skip because it's all known for the HGB equation. So
Sorry, it's only sufficient. Sorry. It's only sufficient condition in general case. It's not necessary condition.
Because I found in the book, he said it's the necessary and sufficient conditions. Maybe I will share you.
That's strange. You can share to me. You can share to me later, but that's strange because it's only in general case. It's only sufficient condition. So maybe it's some particular case. I don't
okay.
know.
Yes.
Okay. But no problem, no problem. Just continue. Okay. Thank you.
Okay. Let's move on. And next, I'm going to explain some idea about the paper which I have learned. The first paper is a dynamic game of emission pollution with uncertainty and learning. There are two key points in the title. The first one is the uncertainty. Uncertainty is it can be the players don't know the information about the mother nature, or they don't know the rate of pollution absorption. And the second one is about the learning behavior of the players. There are three cases of learning. The first one is for information, which means for information, that is the players know the exactly value of the unknown parameters. And the second one is the learning case. It may be our focus. And this means the players do not know some parameters, and they update their beliefs according to the Bayes rule. And the no learning case is an intermediate case, which means the players doesn't know the parameters, but they use their prior beliefs. The last one is according to the Bayes rule. That's the difference. And let's see the model part. ST is the pollution stock. It evaluates by this equation. Eta is the uncertainty, and EIT is the emission of country I. 1 minus G is the natural absorption. And then we turn to the payoff of the player I under uncertainty. It's an expectation. E is an expectation. And delta is a discount factor. And this part is the revenue of player R and time T. And this part is the damage cost. So it's construct like this. And I subject to the pollution dynamics 3. Given the model above, we consider the value function of the learning case. Because we first introduce the Bayes rules in this model. Because I theta vertical eta is the posterior beliefs, and the phi, this one, is the conditional probability distribution, and because I theta is the prior beliefs of the player I. And this one, it should be the beliefs for the parameter eta. And then we can construct the value function VIL. It should be maximize the control of player I among his control sets. And this part is it should be the utility function of player I and the instant time T. Delta is also the discounted factor. It should be the integral among all the eta. And this part is the ST plus 1. And because I hat, it should be the posterior beliefs of player I. This part, it also could be the beliefs for the eta. So this is the value function. And next, we can use the value function to calculate the equilibrium of the learning case. The form is like this one. And the second paper which I learned is the uncertainty and climate treaties that ignores P. This paper is for a two-stage coalition formation game. In the first stage, the countries choose their membership, and in the second stage, they choose their emission strategies. So they can distinguish 3 cases. The first one is uncertainty is not resolved. This is no learning. And the second one is uncertainty is not resolved before the second stage. This is the partial learning. The third one is uncertainty is resolved before the first stage. This is the full learning. I think this model is more complicated, so we will consider it later maybe. And the last part is about the further plan. I will finish reading the paper, Learning and Technological Progress in Dynamic Games, and determine the way to construct HGB equation for the continuous updating. And this one is my question. Should I focus on the dynamic or the differential games? The time should be continuous or discrete.
I suggest that we can focus on the differential games before you already have. So I will just shortly want to introduce. So Jo, she's a master student of the first year. She only applied to SPBU, but we already have one published paper and one working paper for the Pendragon maximum principle with continuous updating. And soon, actually, about the working paper, soon the native speaker soon will help us to finish proofread, and then we can send a paper for publication. So we had some delay, so I cannot influence this.
No problem.
So for differential games, I suggest to consider differential games, and when you finish the second paper, learning and technological process, so I already have during September I was thinking how to accomplish this Bayesian learning and continuous updating, and I came up with a general idea, and just recently I found out that but the problem is that this type of Hamilton-Jacobi-Bellman equation is very hard to construct, very hard, because it is not, usually Hamilton-Jacobi-Bellman equation is a partial differential equation, but it seems that in our case it will be a partial differential and integral equation.
Yeah.
Very complicated.
That's it.
But since it's very complicated, it's interesting to construct and approach and solve. And I think that and I will send you maybe one paper where some people also construct this kind of partial differential integral equation, but not Bayesian, no updating, no, but just mathematically something related. So and I will also communicate with them, because there are some kind of problems how to solve special models. So it's possible to construct, but how to solve models later, this is something also I will need to consider and think how to do it. This is it.
It's no way to consider the dynamic games, because the model is talking about the dynamic case. Because continuous updating
the next paper for dynamic. Okay. Okay, I understand. So actually, anyway, you can read, and it's useful to read paper anyway. If it is about dynamic games or continuous games, because the key point is the same, right? So every dynamic game can be transformed to continuous time game. Any continuous time game can be transformed to dynamic game. But it is important because our aim is to develop something new. So if you want to develop, you need to have some ideas and key points in mind that you can use, right? So, and then at some point, all your ideas can be stored in one packet and one package, and then you make a new result, right? So I suggest to look. And thank you very much for a perfect presentation. That was very nice. Thank you very much.
Thank you.
I think it was great. Do you know when you will be able to come to Russia? Because and it's a question actually for everyone, because I'm not very clear about this thing. When you can actually fly to St. Petersburg?
I'm not sure, actually.
I know. Putin knows how they can come to Russia. Putin.
Okay.
Calling him.
Okay. After the seminar, I will call him to ask, because we cannot wait for such a long time, right?
Thank you. Please call Putin. Okay. Next student is
Okay, it's a joke.
谁呀？下一个是
Hello, Professor.
OK。
Hello.
Could you see my screen?
Yes. But I ask you to be a little bit faster, a little bit fast, so that we could.
Okay. Hello everyone, my name is Yepei Chen. Welcome to my presentation. I will introduce my report from the following 3 parts. In this month, I mainly studied 2 chapters, non-cooperative multi-stage games and cooperative multi-stage games. This is my study list. There are 2 important methods I have mastered: solving subgame perfect Nash equilibrium of using backward introduction and using imputation distribution procedure to solve the time inconsistency of the cooperative solution. And today, the first question I want to talk about is the analysis of repeated game phenomenon. Take the prisoner's dilemma as an example. If the prisoner's crime is relatively minor and each sentence is not very serious, then the 2 prisoners will commit the crime after they are released. Sentenced after the crime, they are committed again after the release. It is the repeated game. In the repeated prisoner's dilemma, the game is played repeatedly. Therefore, each participant has the opportunity to punish another participant's uncooperative behavior in the previous round. At this time, cooperation may appear as a balanced result. The motivation to deceive may now be overcome by the threat of punishment, which may lead to a better cooperative outcome. Therefore, the impact of a single prisoner's dilemma can be offset. And then I designed an experiment to verify this hypothesis. I invited 12 friends to participate in this example. They are divided to 4 groups, each with 3 people. AB is a confrontation group and CD is a confrontation group 2. Using repeated games, a total of 8 games with the same structure are played. After every 4 games, the 2 groups can choose to discuss or not discuss. The next 2 games doubled the reward and penalty scores. In the end, the group with the score greater than 0 is judged to win. This is the experimental rule. There are 2 colors to choose from. If 2 teams choose red, they will each get 3 scores. If 2 teams choose blue at the same time, they will each get -3 scores. When the selected colors are inconsistent, the red one gets -3 scores, -6 scores, and the blue one gets 6 scores. The scoring standard table is shown table 1. The table 2 is the experimental result. It can be seen that Group A has the highest score with 9 scores, followed by Group B and D. And among the 4 groups, only Group A has positive results. And the CD confrontation group wins Group D, and the A group of the 4 groups wins. According to the score summary table, the line chart is drawn as follows. It can be seen from the figure 1 that the scores of the 2 groups A and B are quite different. Also, A and B have a same expect for the first one. And we can see from the figure 2 that the choice of the 2 groups C and D are quite different, and the score situation has been a state of fluctuation. And now we can draw the conclusion that People are more inclined to choose cooperative strategies in repeated games, but in face of high returns, people may also choose to betray. The second question to be discussed is the solution of the matrix game that we have learned before. Today we use the MATLAB program to solve. Here we use the example of Tianji horse racing. The Tianjin horse racing problem is about the horse racing between Qi Wei and Tianji. The rules of horse racing is each time the two sides have 3 horses, 3 games 1-to-1. The loser pays the winner 1 kilometer of gold. According to their strength, their horses can divide it to 3 levels, up, middle, and down. There are 6 sorts of the order of the 3 horses, so each side has 6 alternative strategies, as shown as in the table. When Qi Wei can use strategies x1 and Tianji uses strategy y1. Qi Wei King's pair of matrix. Qi Wei King's pair is 3. Matrix A is the Qi Wei King's pair of matrix. We can add 1 to each element of the pair of matrix A and get the pair of matrix A1 with each element being a positive number. Then turn to discuss the matrix strategy gamma 1 with A1 as a pair of matrix and solve 2 linear programming problems. The above linear programming can be solved with MATLAB program, and this is a program we import the matrix A and we can get the solution X. This is the solution X there. Finally, this is my study plan. I will read some papers related to my research direction. This is the article I selected. The first paper studies the experimentation of the Shapley wheel on the minimal cost spinning trees, and the second paper studies 2-stage network games. Consider both cooperative and non-cooperative settings. In case of non-cooperative, the Nash equilibrium is used as a solution concept, whereas the cooperative setting involves an allocation as a solution concept. It is demonstrated that the Shapley wheel does not satisfy the time consistency property. And the third paper studies the problem of constructing the dynamic Nash bargain solution in a 2-stage game. I think this paper will be very useful to my study. That's all, thank you. And finally, happy birthday to you. That's all. Hello.
Thank you very much. Thank you very much. I think it's very interesting. I think the presentation was very interesting, very inspiring.
Thank you.
Ian, do you have any comments?
Yes. I'd like to explain what she has done in this month. In fact, Ye Peichen and another girl, they are studying our online course, and they have finished first 5 chapters. So only in differential game they didn't learn, but all above cooperative, non-cooperative, dynamics, all important parts they have learned and finished the homework. They did a good job, and but I don't I have advice about her presentation, because the project these examples, for example, Tianji horse racing, it's old story in China 2,000 years ago, and she used the MATLAB solve this problem. It's great, but all above in presentation is simple because they have learned dynamics stability. So I think in the future they should add more complexity things.
Okay, I will do it.
Yes, but this presentation is good.
Yeah, I think very good. I think very good. Thank you very much. Thank you. Thank you.
Okay, thank you.
Okay. Next is Chen Min. She is the last one.
Hello, Professor.
Hello, hello, hello.
Hello, Professor. Hello, everyone. I am Chen Min. Today, I will give a report from the following 4 points. First, it is my study list. I learned this in the past time. From the learning, I know these methods. The first, how to solve the mixed strategy of matrix game. It has 4 methods to solve these questions. And then how to ensure that the players in the biometrics game can get the optimal solution. We can use Nash bargaining solution. The last, how to ensure that the players in the cooperative game can get the optimal solution. About this question, we can set up a coalition and so that all players in the coalition can get the maximal benefit than they are alone, and use the Shapley value to distribute each other. Then I have an example about cooperative multi-stage games. First, this is the problem. Tom needs to go to country and buy books. He needs to transfer 3 times. If he fails to catch up with any transfer on the way, he will not be able to buy a book in the end. First, there have 2 important definitions. One is imputation distribution procedure, and the other is time consistent. This is a diagram for this problem. If Tom wants to get books, he must complete these 3 steps. In this game, the player set is N. The strategy is Y and N. Y means he makes a successful transfer. N means he makes a failed transfer. If all the players choose strategy Y, the payoff function equals 4. If the player 1 choose N, the payoff function will equals 3. Because the player 2 and 3 cannot choose. The player 1 already ended the game in this point. This is the characteristic function. When we calculate this, we must let the game become the zero-sum game, and we will get these values. The imputation set is C, and we also can calculate the Shapley value. Because we have to think about what the players are getting at each step. So there have imputation distribution procedure. We can calculate this. The next time I will read these papers. and learn more about minimal cost spanning tree. Thank you and happy birthday. Wish you have happy every day.
Thank you very much.
Thank
Thank you.
you.
Thank you. Very interesting also. Yeah. I think it's all clear and perfect, right?
Yes.
Yeah.
Um,
Thank you. Thank you.
Yes, she also did all homeworks on online course, and I recommend the book written by Petrosyan and Negavich, Game Survey, second edition, and they read positional game. So they are trying to read more papers in next month. Okay. Oh, we have finished the all presentation. Yes.
Okay. When will they present something about the cost spanning tree?
Next
Maybe
month.
some. Okay.
Next month.
Okay.
好的，大家我们这个报告都结束了。大家有旁听的同学，有什么感想，有什么问题，可以大家交流一下。然后因为今天讨论的时间比较久，耽误了比较长的时间，所以大家有什么想法可以尽快的说。然后崔老师您在吗？
我在，李云。
OK，